Hello everyone, let's go ahead and take a look at our last topic, which is called first order differential equations. Now, a differential equation is an equation which connects the derivative or derivatives of an unknown function to the variable in which the function is defined and may include the function itself. Now here's a couple of examples of differential equations. We have 2 d of y over d of x plus 3y is equal to e to the negative x. And we also have this one here, which is much simpler. We have d of y over d of x is equal to y plus 1. Now, what is the solution of a differential equation? Well, the solution is just going to be in the form of y of x. And it's going to satisfy the differential equation for all x, x being an element of the domain. Now, what is the form of the first order differential equation? The first order differential equation, not just a differential equation, but a first order differential equation, is going to have this form here. And the thing that we have to recognize is that there's only going to be one derivative, so this right here, and it's only going to be the first derivative. So if we take a look at these two examples here, these are examples of first order differential equations. First derivative and only one derivative. First derivative and only one derivative. Now, I'm hoping that this is going to look a little bit familiar to you in terms of how we actually solve these type of first order differential equations. We actually used the separation of variables. Now, if I went ahead and multiplied both sides by d of x, and then I divided both sides by y plus 1, I would have d of y over y plus 1 is equal to d of x. I integrate both sides, and then I can go ahead and solve for the function that would represent its solution. Now, let's say, for example, though, that we have something here, and notice that in this case, we're not going to be able to actually separate the variables. Now, for the purposes of what we're doing right now, let's say that this is a possible solution. How do I go ahead and tell whether or not this possible solution is actually a solution to the original differential equation? Well, what I need to do is I need to go ahead and substitute the y here, but I also need to substitute the d of y here, so I need to find out what d of y over d of x is, and here's that. And if I was to go ahead and take that, substitute it into the original first order differential equation, I come up with this, which simplifies to this, which simplifies to this, and therefore I know that this right here is not a possible solution, but it actually is a solution. And it's going to be a general solution, because notice that we have a constant of integration there. Now, what we're also going to have to deal with is what is called a slope field. Now, what is a slope field? A slope field is just going to be a visual representation of the tangency lines to the family of solutions to the differential equation. Now, remember what we said is we're going to come up with a solution here that has this form. Oftentimes, it is going to actually have a constant of integration, which means that we're dealing with a family of functions. Now, all of these functions here are going to be solutions. So we're talking about a family of functions which represent the solutions to a first order differential equation. So now how do I go about generating this? Like all these green lines, how do I generate these green lines? Well, basically, if I just go ahead and take a look at any particular point, let's just say, for example, 0, 0, it says that the derivative, or the slope, the instantaneous rate of change, the tangency line of the particular solution, if it were to go through 0, 0, would have to have a slope of 0 plus 1, which is 1. So, notice that all of these values here, all of these green lines that are on the x-axis, all have a slope of 1, because that's what this says. d of y over d of x is equal to y plus 1. All of the values of y on the x-axis is going to be 0. Therefore, all of those instantaneous rates of change, which would be tangent to particular solutions of this particular first order differential equation, would have to have a slope of 1 at that point. Now, it's the same for all of these other values as well, because this would be 2, this would be 3, and this one here would be 0, and this would be negative 1. So what that means then is that we're actually going to be able to generate, given a particular solution to this particular first order differential equation, we would actually be able to come up with one particular solution, which would then, if we graphed And say, for example, if it went through this point, negative 1, 0, the tangency line at that point would have a slope of 1. Okay? Now, the best way to go ahead and determine what the solution is looking like and how that relates to the slope field is to be able to use our graphic display calculator, or even to go ahead and use our computer software to go ahead and show how the slope field actually generates us a visual interpretation of the general solutions to a first order differential equation. Now, we'll go ahead and take a look at that in class. So again, just to wrap things up, we have a differential equation which we've actually worked with before, but we never talked about it in that way. We know that the solution is going to be a function. The first order differential equation is only going to have a first derivative and only one derivative in the equation itself. We actually did use separation of variables before to go ahead and find the solution. But if we can't find the solution and we're given a possible solution, we now know how to go ahead and determine if that possible solution is actually a solution of the given first order differential equation. And we have an idea of what the slope field is in terms of how to generate it and how to interpret its relationship to the actual solution and how it's generated by the differential equation itself. Okay, so again, we'll take a look a little bit more about this because we need some of the computer software to help us look at that and investigate that a little bit more. But I think we'll go ahead and have a much simpler time dealing with some of those initial questions there. So, see you next time. Bye-bye.